Yeah, welcome everybody. Welcome to today's lecture. We will talk about NoSQL databases or NoSQL databases today. NoSQL databases are different from SQL databases. So what we mostly use and mostly learn about databases is relational databases. You use create table commands to create a table. They have a fixed schema, and then you insert, update, delete, and select data from that table using the commands. The benefits of this structured data is that your application knows the schema of the data. And in NoSQL, it's quite different. They offer flexible schemas. They offer different data models than the relational models using complex types, graphs, documents, and so on. Many things you know already from relational database systems were added there too. So we have JSON support, we have XML support. In a few weeks we will talk about graph processing within a relational database using recursive queries. So imagine a query where you use in a view, in the from clause of the view itself. Yeah, not as a view, but a common table expression. This is used for graph traversal. We'll do this in some weeks. This week and next week we will talk about NoSQL databases in general. I show 4 examples because most people fit the NoSQL databases in 4 categories, and yeah, we will look at those 4 categories today. This should be just a very compact overview, because this is not a lecture about NoSQL databases. Some of you already attended a lecture of NoSQL databases. I want to show you the fundamentals of NoSQL. What is NoSQL? What are typical systems? How do you use them? And just the basics. And the goal is that you know these systems and that you know when to use which system, and compare those, evaluate those, and compare those against the other approaches that we use in the lecture. Okay, are you there? Write hello in the chat. Say hello, otherwise I think I am talking to myself. There we are. Yeah, nice. Okay, that's much better. Do you have any expertise in NoSQL? Please give me the answer, not in the chat, but go to frage.de, Frage with 2a, and please answer the question, do you have any expertise in NoSQL? So, how many attendees do we have today? 30, 35. So let's wait until everybody answered. Two people of the 35 is me. So 30 is a good number. Yeah, what do you have? No expertise. Yeah. Okay, some people used a NoSQL database from work. Can you please write in the chat which one did you use there? Also for the private interest people, which ones did you use from the from the NoSQL databases for your private project, and for the ones we see, only a smart fraction of people attended the NoSQL lecture. So for you, the yellow ones, there's not so much new, but a bit. And of course, this chapter is relevant for the exam. Can you please write? Yeah, there's one answer. MongoDB was used from work or in a private project. Which systems do the others use? I wait for your answers. Okay, this is a nice cartoon from geekandpoke.com. I like this cartoon a lot. Do you have any expertise in SQL? So they are currently writing a CV. No? Then simply write expert in NoSQL. So that's a bit a joke, that you can write expert in NoSQL when you don't have expertise in SQL. But we all know SQL does not stand for NoSQL. NoSQL does not stand for NoSQL. Here we see the meaning of NoSQL. So NoSQL in the 1970s could mean we don't have SQL. We have no SQL. Of course, that's not the meaning of NoSQL, and nobody used the term NoSQL when there was not yet SQL. Then 1980, there was the language SQL. Basically, the language SQL was already there 1970, but maybe 71 or something. Yeah, it was not yet so popular yet. But 1980, the people could say, we know SQL. In the 2000s, there was this hashtag or buzzword, NoSQL. So vendors of new kinds of database systems had a conference and a meeting, and this conference was called something with NoSQL, and that was the new term, which means we have a database system that has a different data model than the relational data model. Before 1970 and between 1980 and 2000, there were also database systems which used different data models. For example, 1960 something, there were network models which model the objects like objects in a programming language. Then there was the hierarchical model and XML databases and so on. So we took a look at base X in another lecture. These are older than the word NoSQL, but nobody told them NoSQL. NoSQL were the serious database systems which began to use by big companies like Google, Facebook, Twitter, and many other web-related companies. One person in the chat uses MongoDB, CosmosDB on Azure, and CouchDB. Yeah, Azure is a cloud platform. So 2000, I think this... When did AWS start? Amazon Web Services. I think, yeah, launched in 2002. Yeah, so Amazon Web Service is a cloud vendor. There are other cloud platforms like Azure or Google Cloud or Ali Cloud from China, and these cloud platforms offer database as a service. Yeah, you could say they offer a platform as a service, and databases are part of that platform. It's not database as a service, but you don't have to install the database and update it. You can simply use the database that is there. And AWS has DynamoDB, and Azure has, I don't know, is Cosmos DB a database that's made by Microsoft from the Azure platform? I don't know. And there are so many systems. We took a look at dbengines.com at this ranking here, and yeah, the first four the four most popular database management systems are relational database management systems: Oracle, MySQL, PostgreSQL, Microsoft SQL Server, and so on. And then there are many document databases, key value databases. So this is all NoSQL, graph database, Neo4j, and so on. Okay. So in 2000, NoSQL was, the meaning was, yeah, we don't use SQL. Then, and that's today's meaning of the term NoSQL, it means not only SQL. So it just tells you that there's SQL, and SQL is still important, and SQL is still the standard. But there is not only SQL, there are more. And then in 2013, people thought, why do we really need to jump on that NoSQL train? Isn't a lot of that also possible with SQL? So this NoSQL, in German you would say doch, shows two directions. First of all, the direction, in SQL we have extensions for JSON and XML. So in SQL we can use some of the benefits that NoSQL databases have. So when a MongoDB person says, in MongoDB you can store arbitrarily structured JSON documents, then Oracle and PostgreSQL say you can also store them in Oracle and PostgreSQL. Simply create a column of type JSON. When NoSQL says we are scalable, we have distributed databases, Oracle is also a distributed database, and many relational data warehouse systems are also relational and also scalable and distributable. So the benefits that we will learn are also added into the SQL world. And on the other hand, there were approaches that bring back SQL to NoSQL databases. So it's possible to write SQL queries on MongoDB and write SQL queries using JDBC and so on any kind of NoSQL database, because people wrote wrappers. They said SQL is so nice, bring it to the NoSQL world. So that's not a typical usage, but that began. And there are approaches like Apache Hive, which allows writing queries in a language very close to SQL to big data. That's in Apache Hadoop. And there are databases like the white column store Cassandra, which has an SQL interface. I call it SQL interface. They call it CQL, Cassandra Query Language, but it looks like SQL. Okay, let's come to the typical properties of NoSQL databases. I wrote some of the most important ones here. So this is in the same order as the list on this DB rankings table here. So what we have is MongoDB, the most popular NoSQL database. It's a document store. Then we have Redis that we will look at today. It's a KeyValue store. I skip Elasticsearch. We have Cassandra here. It's a white column store. DynamoDB is multi-model, so they say it's a document store and a key-value store. So basically, yeah, it's a mix of different families of NoSQL databases. And then we have a graph database here, Neo4j, and another white column store, HBase. My examples use HBase, Redis, MongoDB, and Neo4j. MongoDB, Neo4j, Redis is clear because they are the first ones in their category, the most important ones in the categories document, key value for Redis, and graph Neo4j. And I use HBase and not Cassandra because Cassandra is so SQL-ish. And this here is DynamoDB. Okay, typical properties. Typical properties. This is not a real must criterion for all relational database, NoSQL databases. For example, Neo4j is very bad in distributed processing because Neo4j stores graphs, and in graphs everything is connected to something else, and this is really hard to distribute. But Neo4j supports distributed storage. This is, they support it. But the others, their distributed storage is built in from the very first minute, and they are very good scalable. So distributed storage, we had this in the beginning of this semester, means storing part of the data on this machine, part of the data on that machine. So when the system gets too slow, then simply add more machines and then redistribute the data, and every machine can process the data that's on that machine. That's what we call distributed computing. So you ask a question, a query, and this query is not executed on a single node that pulls the data from the other nodes. The query is processed close to where the data is. So when we say, give me the sum of all product prices of the category food, and all products are stored on different machines, then machine 1 is asked, hey, do you have products of category food? If yes, please give me the sum. The same question is told to the second machine and to the third one, and then in the end a grand total can be computed based on this partial sum. So every machine can help in computing a complex query. High horizontal scalability. We had the terms vertical scalability, scale up and scale down, meaning adding more RAM, adding more and better CPUs to a machine to improve the speed of a single machine. Horizontal scalability, scale out, means we add more nodes to a cluster to improve the performance of the whole cluster. And this is basically unlimited, and this is very nice. So we don't have any limits. All the NoSQL database management systems you see here on the right, and many more, are open source. So I said Oracle is also a distributed database, but Oracle is costly. So when you want to do the same things with the same horizontal scalability, you may buy an expensive Oracle license. And when you use MongoDB, it's for free. And Redis is also for free, and you have all the benefits without any cost. When you use these tools in the cloud, then of course you have the cost of the cloud platform. So most NoSQL databases are open source, and that makes it cost effective. A typical property is also the schema flexibility. You don't use create table commands to create a table with a fixed schema. The schema is flexible. We will see on the HBase example, you can create a table, yes, but this table can have arbitrary columns. When you insert data, you say the product price is $2.50. Nobody needed to create a column price. You simply set it. In MongoDB, you store JSON documents. You simply insert an arbitrarily structured JSON documents. NoSQL databases are using a semi-structured data model. Semi-structured means the metadata is part of the data itself. That's because of the schema flexibility. Like in JSON, where the metadata, like price, $2.50, price is basically metadata, but it's part of the data itself. And there are many NoSQL databases which are optimized for unstructured data, where you can use algorithms to do machine learning, for example, on text data or image data. A typical property, of course, is that NoSQL databases use a different data model than the relational data model. So they have another data model. Some people say the data model of NoSQL databases is much more simple than the relational data model. For example, Redis, a KeyValue store, is like a hash map in a programming language. It's a much simpler data model than the relational data model, where we have tables with columns. But when we take a look at Neo4j, this is a much more complex data model. So we have interconnections between data items. We have graphs here. Okay, let's come to the 4 categories of NoSQL databases. KeyValue stores, the data model is a list of key value pairs. So we have a key and we can ask the database, give me the value for the key. So this is like a hash map in Java. So I have a key value store here, J shell, my Java shell, and I say map string int key value store. So a new hash map. Of course, it's called integer. Then I add. So what can you do with a hash map? You can put something there. Put so what do I want to buy in the supermarket? Tomatoes. 5. Okay, and I want to buy bread, 1 bread. Oh no, I need 2 breads. So when you put something there, that's already there. The key bread is already used, so I override it. And then the second thing I can do is I can ask for a value by specifying a key. Give me bread, and it gives me the number 2. Okay, that's basically also the principle of a key value store. You you put new data items, providing a key and a value. And when you ask for data items, you provide a key and you get the value. You cannot make queries based on the value. Give me all items that have a number larger than 4. That's not possible. It is possible by iterating over all items, but you don't want to do that. This is not performant. A hash map uses a hash structure here in Java. And hashing is very efficient. You use a hash function to create the hash of this key, tomato, and then this determines where the key value pair is stored. And the same principle is also used for NoSQL databases. And you can also imagine that this hash function on a distributed database tells you where the key tomato is stored and where the key bread is stored on which node on a cluster. On a wide column store, we have multiple tables. And in each table, you specify a row with a row ID and arbitrary columns. So when I say in the table people, there is the row with row ID 100. I want to know the value in the column name. Or you say in the table people, there's a row ID 100, give me all data. That's also possible. So give me the full row. And the thing that differs wide column stores from relational databases is we have a row ID. So this is very typical here. And this is used for distributing the data over the cluster nodes. And this is used for accessing the rows. So the same as for KeyValue stores, we cannot use complex queries or queries on secondary columns like give me people where the first name is Peter. This is not possible. It is possible, so but not efficient. Then we have document databases. In a database, we can have multiple databases. We have a collection. So in each database, we have multiple collections. And each collection is a set of documents. A collection of documents. And this document is typically JSON. Graph databases. There the data model are vertices which are connected via edges. And the data you can store in the vertices, so-called properties. Again, this is an arbitrary list of properties which have a property name, for example, price, and a value, $3.50. And in edges, you can also store data. You can store properties not only in vertices, but also at edges. We take a look on this next week. Now, I want to introduce to you the KeyValue Store Redis. So it's a very simple database, which is not used as an alternative to relational databases. For MongoDB or Neo4j, you could say, this can be my one and only database for this and that project, because you have everything there that you need to let applications work with that database. And in Redis, you're very limited. The data model is very simple and it's only made for specific use cases. So the people who use Redis use it only for one or multiple special use cases. So it's there to accelerate their existing database. So you currently have a PostgreSQL database and this database gets too slow. Then you analyze, there's a lot of queries which say, give me the video URL for a video ID. Stupid query. Then you simply put that in a Redis database. The key is the video URL token, and then the value is the video ID or something. Or a lot of queries count how often a video is clicked, and a lot of queries check whether the current user already watched the video or not or something. And for these special use cases you can use Redis, because Redis is not just a key value pair, a map of key value pairs like here, where the key is of a atomic data type and the values of an atomic data type. The value can also be again a hash map. So then we have a two-dimensional hash map, and then we have again something like a white column store, where each row has arbitrary columns, because the column of the row tomato can again be a hash map with column names and values in that column. Or you can use a set. So what I told you now with the two-dimensional hash map is called hashes in Redis. You can store a set of values. So you store for a video the set of user IDs who already watched the video. That's possible. So key is the video ID, and value is a set of user IDs that watched the video. And then you can quickly add something to the set when user 15 watches a video. You can check what's the cardinality of this set, so how many people watched the video, and you can check, did a specific user already watch the video, yes or no. And Redis is optimized for these kinds of queries. It's very limited what you can do with it, but that what you can do is very fast in Redis. Lists are like sets, but here we have duplicates, and here we have an order. In sets we know we don't have an order, and we don't have duplicates. Sorted sets are sets where each element has a so-called score. So you put elements in a set, and for each element you specify a score. For example, how often did a user watch that video, and then you can increase the score and then order by the score. And again, Redis stores these sorted sets in a way that you can efficiently ask for the top k elements with the highest or lowest score, giving all that have a score greater than that or smaller than that. This is a special kind of data type in Redis, which I've never seen somewhere before. The most simple data type is called string. It does not only store strings like text data. With string we basically mean byte array. So it is any kind of data. You can store a number, you can store true or false, a boolean, you can store a string, you can store a whole video binary data. So basically you can store everything as a string. Some people store JSON documents in a Redis document, in a Redis database. So we have a key and then a JSON document for that key. Then it's basically a document database, but you cannot make queries on that JSON document. This is a very simple example. We set a to 9, then we use a get command, we get 9 and increase a. Redis has a sandbox for trying it out. Try Redis.io, and there you can say set a9 and then get a, and then you get the value. And you can also say set a hello or something and get a, and it gives you back hello. And in the first exercise you connect a program in a programming language of your choice to a Redis database, and you see how to make these commands here in, for example, in Python or Java or whatever language you want to use, because here it looks like a query language. Oh, in SQL you say select star from, and here you say set, but actually you don't write a query here. When you really work with an with a Redis database, you have a method called set that you can then call. So different from SQL, when you work in a program with a relational database system, you have something statement dot execute query, and then your query itself is a string. So the database first of all has to parse the string, see what is meant by this query, optimizes this query. Can I use an index? Is there an index? No. And in Redis, so this is SQL, and in Redis you ask Redis command directly by executing the methods. So when R is your Redis database, then you say A is 9 or something to execute this command here. For lists, we have operations rpush, lpush, lrange, rpop, lpop. So before I explain those, so you don't have to specify that the key seasons is a list or that the key A is a string. It is automatically determined what the type is depending on which operation you use on that key. So when you set A to 9 and then use so A is 9 and then use an rpush, then you get an error operation against a key holding the wrong kind of value. So this works for new key value pairs, but not for the existing one, because this is already a string. You cannot add an element to something which is not a list. Yeah, I want to know from you, what do you think does the L in lpush and lpop mean? So I don't have lpop here, but what does it stand for? What do you think? Go to frage.de, frage with 2a, and give me the answer. Again, I wait until 30 people answered. Lpush, seasons, spring. Does the L stand for link, for loop, for list, or for left? If you don't know it, here's another command, rpush. So what could R stand for? L and R. If you have a PlayStation controller or so, or Nintendo, then you have L and R buttons. So L stands for left. Oh, there it is. Yeah, 2/3 answered it correctly. L does not stand for list. It means put on the left of that list this new element. And R push put at the right of that list this new element. So a list is an ordered set of strings. So for adding something to an empty list, it doesn't matter whether you use rpush or lpush, but when something is already there, then of course it matters. Do we add the new element to the left of the summer? Then the list would be spring summer. And if we would also use rpush here, then we would add it to the end of the list. Then the list would be summer spring. So you can use it as a queue. Let's say we have a printer that uses Redis, or we have many printers. Printer 1, printer 2, printer 3. And each printer has an ID, that's the key of the Redis store, and then we have a list. So I want to print a document A, and I use rpush for that. And then another person wants to print document B on the same printer, and my printer uses first in, first out approach. So I use rpush to add something on the right at the end of the queue, and the printer uses lpop. Lpop removes something from the list. So we can try out lpop. So I rpush printer 1 document A. Okay, then I print document B, and my printer then says lpop printer 1, and it gets back document A. And this is now also removed from the list. So pop shows you an element, this case the first left element, leftmost element, and it is also removed from the list. And there are other so docs Redis commands. There you can say which data type do you want to work with. We had strings. There you can say, okay, I want to clear a specific bit in that string data. We saw get already. We saw increment, to increment it if it is a integer. Increment by something, set the string to the value. Yeah, this is boring, but let's go to lists. And for example, here, get the length of the list. How many elements are there? If you would use a relational database management system, you would model this as a table with yeah, basically two columns. Printer ID and yeah, no, three columns, because the order is important. Printer ID, then a number, which is always increasing, or for example a timestamp, and then the value of the document that should be printed. And if you want to ask how many documents are there for printer 1, then you would need a count star with a where predicate or something. For this you can use an index, but yeah, it costs something. And here for Redis you will see almost all operations are in the complexity of O of 1. So it does not depend on whether you have 1,000,000 key value pairs or 1,000,000,000,000 key value pairs. It takes the same time. In the relational database, of course it matters. Because of the index, it's still cheap in logarithmic time, but constant time is better than logarithmic time. And it does also not depend on the number of elements within the list. So independent whether here are a million documents in that queue or only 5 documents in that queue, determining the length takes always the same time. And you see this O of 1 for very many operations. So you have to find very specific, go to a sorted set and then count, remove and return members with the lowest score. This sounds complex. Yeah, okay, here you see O of log n times n, where n being the number of elements in the, but if you would do this in a relational database management system, it would maybe be more costly here. So Redis is optimized for this built-in operations on the built-in data types here. Another data type is a set. So basically it's like a list, but you cannot add something to the left or to the right. You can just add something. So it is called sadd. S stands for set, and you add something to the set. And I show you here that in many applications the key in a Redis store is often structured into multiple parts. For example, here I chose that the key is pers:5:hobbies, and then you can add something to that set of hobbies of person 5 with this sedadd command. Again, you cannot say give me all the people that have the hobby piano and so on. This is just optimized for a key-wise access. So tomorrow I want to again say, give me the number of hobbies of person 5. Card pers:5 hobbies, 1 hobby. Give me all the hobbies, give me 1 hobby. Is yoga part of the hobbies of person 5 as is member? No. So it's only optimized for key-wise access. And printers are not using Redis, but queuing systems, for example, of web search engines, they use it like this. For example, you can imagine Google or Bing have a crawler, and they store for each worker node. So like here we had the printers, we have a lot of working machines, let's say 50,000 workers. We store a list of documents which should, or a list of websites which should be crawled. And crawling means you go to that website, look into the source code of that website, find all links, and for each link that you find, put it again in one of the queues, so that they are always crawling and working and analyzing the whole web. Hashes are values that again are maps. So here you can use HSet, you specify the key, and then the key of the second dimension, because the value is again a map with keys and values. So this is the Redis key, and this is the key of the map, city, and this is the value. So with a hash structure, you can store something which looks like a table. Person 1 lives in the city London. Person 1, and then another column, is born in 1979 or something. And when you say hget, and then for the key a specific, I call it column, then you get the value in that column, in that row, and hgetAll gives you all columns with their values. Of course, they are not called columns. These are, again, key value pairs. So, one exercise for you. Each product in a web shop can have arbitrary properties. So the product can have a weight, an author, a color. Books have authors. Ebooks have authors, but ebooks don't have a weight. So specific properties for which are arbitrary. Which Redis data type would you use to store those? Go to frage.de and yeah. Yeah, sorry. Product number 1 has the color blue. Product number 1 has the author Peter. Product number 2 does not have an author, but different properties. Which data type would you use here? In between, I again go to redis.io, download it, Redis 6.23. Yeah, Redis only runs on Linux, but we in this exercise about Redis, it's not required to install Redis. So you will access a cloud database. So you can solve the exercise with any operating system. But what I do now here is Redis on Linux. I unzip Redis and then I have it here. Install C readme. I think it is okay. Let's look at the answers here. We want to store arbitrary properties for each product. So each, I want to say row, each key is a product and each value is a hash of properties. So most of you answered it correct. String, yeah, then you need to store a JSON string, or what do you mean by that? But here you can do some special things when you use a hash set and not a string. For example, you can say, I want to only know the property author and I'm not interested in the others. When you use a string with a whole JSON, then you can either query the whole JSON or nothing. List, is not well suited, and set also not. So a hash makes sense for that. Okay, it is still installing. In between, I go to the next database, and the next family of NoSQL databases I want to show you are KeyValue Stores. And the KeyValue Stores are very similar to this hash data type in Redis, because we have a key. In HBase we call it the row ID. So each table has a row ID column. Basically it's not a column, but when we talk about tables, then what else should it be? Yes, a row ID column and then arbitrary columns. The idea came from Google's Big Table. they organized all their web index they crawl for the Google search engine into a Google Big Table. And this table looked like this. Okay, I crawled the website othregensburg.de, and we extract first of all information about that website, because when I use a search engine I want to display that on the search results page, and this is maybe used for filters later on, or I also want to display that or make a complex analytics afterwards. So we store the properties of that website into arbitrary columns. And other websites have other columns. Let's say we have a website about a book, a product website of a specific book. Then you can store the price directly here. Or you have a website about a restaurant, then you store the address of that restaurant. OTH Regensburg may also have an address, but the website of the book does not have an address. So this is very good to be schema flexible here. Each row, which means each website that we crawled, has arbitrary properties. And in the very first version of Bigtable and the very first version of HBase, HBase is basically the open source version of Bigtable. No, not version, but Google wrote a paper about Bigtable. Hey, we created a NoSQL database to store arbitrary columns, and they have a row ID, and we have column families and so on. And then developers made an open source project with the same data model and the same way how to distribute the data on a cluster, and same way of accessing the data and so on. Column families are there to distinguish different concepts. So basically we can make arbitrary columns. But the info column family, we can say, stores the information about a website. And then we have a separate column family storing the outgoing links. Because some applications, like the search engine, is only interested in this information here. And some algorithms, like calculating the page rank, this means the importance of a website by calculating how many websites are linking to mine and so on, they only need to process links. So they distinguish the columns by creating multiple column families and then putting different information in different column families. There's an HBase shell where you can write commands, like in the Redis shell that we saw on the Try Redis website. But again, typically you work with HBase in a programming language, for example Java, and then you use the create or put command in the Java application, and the put command has takes the information in which table do you want to put information in which row. So this here is the row ID, and then you specify a set of columns together with their values. And we see here that each column has the prefix of the column family in which it is. So when you create a table, create websites, you specify the column families. That's all. You don't specify that each website has a title and a language and so on. You only say we have an info column family and a links column family. And the best thing is when you work with HBase is to forget everything that you learned from relational databases. From a relational database, a column title makes absolutely sense, and a column language makes sense, where language equals German is in the query. But in a relational database, you would never call a column www.stwno.de. This is not a column name, but you can now use column names for storing a set of data. The set of links is stored in the columns that have the column name of the link. Why not? This is possible. We are very flexible here. We can then iterate over this set of columns to get all the links. We can count them and so on. What do you think? How does HBase distribute its data across the nodes of a cluster? Go to frage.de. I want to know from you, how does HBase distribute the rows? So here we have only one row, but let's say this website crawler crawls trillions of websites and we have a very big table. Big table in two senses. Many rows and wide columns. So it is no problem that a row has a million columns. In a relational database, you would never have a table with a million columns. Some databases have a limit. You are not allowed to create 1,000 columns. 1,000 is okay, but I think for some database management the limit is about 4,000 or so. But nobody does this. Please don't do it. But in wide column stores, it's absolutely fine to have thousands or millions of columns. Here we have 1,000 links, maybe many information about that website in arbitrary columns. Does HBase do range partitioning on the row ID? Or do you think that HBase makes hash partitioning on the row ID? Does it store each column family on a separate node? The info on node 1, the links of all websites on node 2? Or do you think that all data is stored on all nodes? Node 1, node 2. Let's add a third one. Node 3. These are 3 machines in a network. In HBase they are called region servers. And in HBase you also need an HMaster, which is a entry point for writing queries. So it does not store any data. The data is on the region servers, but the get command, the put command and so on is in the master. And you can specify multiple masters so that it scales and that it is not a bottleneck and you have high availability. I show you the solution here. HBase uses range partitioning over the row ID. So most of you said hash partitioning. Hash partitioning would mean you calculate with a hash function where each data stored. And I show you the benefit of range partitioning here. So range partitioning means all rows that start with A to K are stored here. From the row IDs L to T is stored here, and from U to Z is stored there. Of course, when everything starts with www, then it makes more sense to make other range range don't know, limits. But range partitioning now has the benefit that we can also search for prefixes, or ranges. So give me all websites that start with othr.de/ and then something. So hash partitioning would allow you something like this: row ID equals that one. Now you can say greater or equal that one, and row ID smaller than othr.df. Okay, this would give you everything that starts with othr.de. And this is very nice because you can then structure your row ID in a way that you have efficient range-based queries. One example later. I keep this. In HBase, there's one feature called versioning. I show it to you in this lecture because we will talk about temporal data management in SQL in several weeks, and there is an NoSQL database management system, HBase, which uses temporal data management, which uses versioning of data. So you have access to the timestamp when a specific value is stored, and you have access to previous values of a column or a row. So the actual data model of HBase is we have a table, we have multiple tables, and in each table I specify a row ID, and what I get for that row ID is for each column family and for each column in that column family a set of timestamps. For example, today at 5 o'clock and yesterday at 12 o'clock and last Wednesday on 6 o'clock. And then for each timestamp, the value that was on that timestamp. So whenever I change something and multi-versioning is enabled, I create a new version with the current timestamp and the new value. So it is still possible to ask for the value that my column had yesterday in the morning or so, to make a historical queries. And furthermore, I can read the timestamp. Oh, today the price of the dishwasher tabs is $3.99. When was this value written? Oh, this value was written yesterday in the morning. So it means that yesterday before the morning it had a different timestamp, or maybe it had a different price, that product, or maybe it had the same price but we updated it anyway. Don't know. So you can ask when was the value written. Each column can contain multiple versions of its values. By default, versioning is not activated. Here, see how to activate it. We create a column family info, not simply by saying info, no, by saying the name should be info and the maximum number of versions should be 9. So we specify the maximum number of versions. So when we store 9 historical values and we change it again, then the oldest information is discarded. I don't know if there's an infinity or something. I think it's also possible to get an infinite history, but I'm not sure about that. The default number of versions is 1, so no history, because it takes space. But in any case, each value that you store in HBase is always annotated with the timestamp of its last write. Here's a question in the chat. Oh, yeah, multiple questions. Why didn't I see it? My chat did not. Now I see it. So the question about HBase. Wouldn't hash-based partitioning give you a more even distribution between nodes? No. The magic in range partitioning is choosing good choosing good ranges. So we don't say from A to K, but we choose the upper limit and the lower limit of each range, so that the distribution is evenly. And yeah, let's say you insert many values here, then we simply change the range border from A to K to A to J, and then here from K to T. So the values that had K has to be moved now here. So repartitioning must be done in that case. But yeah, that's okay. And there are other tricks. So for example, in reality, there is not just one range. So you have 20 ranges here. So this node has from A to J, and from this to that, and from that to that, and this is all mixed over the nodes, and this makes it even better distributed. So not just one range, but multiple ranges. Maybe I can open HBase admin tool next week. HBase is not nice to play with. HBase is made for a big cluster and not for laptops with a small amount of RAM. So it is not fun working with it. But I can show you, the admin console shows you for each node, on this node stores the following ranges of rows. It has a very good distribution. It means that lookups by the row ID take logarithmic time, right? Hash would be constant time, and if it has a tree on the row ID, and I think this is the case, then yeah, basically you need a tree to find first of all the node where a specific row with a specific row ID is stored, and then within the node again a tree structure to find where the row is stored. Yes, it is logarithmic time. Like in relational database systems where the primary key is has an B+3 index. Yeah, that's better in Redis. That's in O of 1. Here's an example of how to work with HBase in Java. So this is just for connecting to the HBase database. In that in a configuration file, we store or in a configuration object, we store the information of the server, username, password, and so on. Then we are connected. Then we can reference a specific table. So I want to work with the table websites. A get object is there to get a specific row, because a get, so you could now say, okay, why is get a class? You could say table.get and then this value here as a parameter, like in Redis. But you can say in this get object max number of versions, only for timestamp, blah blah blah. So you can specify more properties of that get. I'm only interested in the column family this and that, so only a projection, only for that. So you put everything in that get object here by using methods. In the Java doc of HBase, you find everything. So you specify the row ID, and here you see HBase does not have any data types. HBase uses byte array for everything. So the row ID is a byte array, each column value is a byte array, the column name is a byte array. So the application is responsible for converting integers to byte arrays, strings to byte arrays, and vice versa, and so on. And you can then say, for example, I want to get the row with the row ID otrh.de, and I want only set time range, only those versions between this and that timestamp, or only that version that was present at this timestamp here. A filter class is, for get it does not make so many sense, but for scan, then you can specify a filter. For example, give me only those which have language German. We had the column language here. It is expensive, but with this filter it is possible to do such kind of predicates selections directly on the database nodes and not in the Java. Yeah, and the function getMap, it is not in the get, it is in the result class. In the result class, that's a class what is returned by a get. And there you can say getMap, and this has this nice return type, a map, where you find the column family, and for each column family, again a map where you find a column, and then for each column, again a map where you see the timestamp and the value in that column that was active in that timestamp. When you don't, when you are not interested in timestamps and you access only the current one and timestamps are not important for you, then get no versions map removes one dimension. So then you can iterate over the result with a loop on that multi-dimensional map here. Okay, let me take a look on that Redis now. We have now I just want to start the server. Where is the script? Oh. Where is the script? I need Redis server. But where is it? Redis server in the src directory. Okay, Redis server. Now ready to accept connections. Redis is now running on port 6379. So Redis is a database like many databases that run as a server process. And now I can write an application that connects to localhost 6379 and work with that database. Or in that Linux archive, there's also the tool Redis CLI. Is it also in the src directory? Yes, CLI, command line interface. And so here my Redis database does not have any authentication. So we have here the redis.conf, where we have all configuration options, and here's also we specify the port. Protected mode is enabled, which means I can only connect as localhost, so nobody sitting in a different room connected to the same network can access my Redis database. And here's somewhere authentication or password. Yeah, you can set a password, and then you need to specify this password here. So you say authenticate, and then you say the password, and if a password is required, you can use it like this, or authenticate and then a username and then a password if you have multiple users and passwords. So you can connect, but you cannot make a GET request or something when you're not authenticated. Then you need to use the auth command here. I want to store now something in the Redis database. Let's say I use my L push printer1 has document A. I use R push to put it on the right. Okay. And another client can then also say L pop printer1, and then I get doc A. And when I again use this, it is null. and there's one version of lpop called blocking lpop, which timeout, let's say 1 day. Okay, this command here returns nothing. It is blocking, it is waiting. Can I verselbstständigen? Okay, and as soon, so this is now my printer listening on that list P1, and when I put something now with a rpush command, as soon as I push it, then my other client now sees the document and immediately removes it. So this client here is waiting for new elements in that list, and this client here is putting elements in that list. And this is fun working with Redis here. So we take a look at the examples next week. I'm so often over time in this lecture. Let's finish now for today. You can do an exercise with Redis. Next week we take a look at some more examples from HBase, and then MongoDB and Neo4j. Okay, do you have questions? Which operating system do I use? This is Kubuntu, KDE version of Ubuntu. Will I be able to do homework without Linux? Yes. You don't need to run a Redis server. I am running Redis in the cloud and providing you the connection data on the exercise sheet. And yeah, I already pushed data in that Redis database. So you cannot do the exercise without that. Otherwise you don't have data. Okay. So you can write a program with Windows, Linux, Mac, whatever programming language you want to use, Python, Java, whatever, and connect to that Redis database. What's your recommended setup to doing the Redis exercise? Quickly set up via Docker locally. As I said, for solving the Redis exercise, you develop a tool that connects to the Redis database. You don't have to run a Redis database. Okay, then see you next week. The exercise sheet will be uploaded in a minute. See you.